So we've just seen that a spectrum is generalizable if and only if it's finite. We want to now we want to describe the dual. Well, we know from last time dx is the internal harmon to the monoidal unit, which is the sphere spectrum, very well. But still, well, what is it? Okay, so suppose X is the suspension spectrum of K where K is a subpolyhedron of Sn with respect to the standard PL structure, for example. Well, then the claim is the claim is we are able to identify the dual spectrum with okay, let me let me write plus infinity here, which means we take the suspension spectrum and then apply sigma to the n minus 1, minus n minus 1. Very well. So we want to prove this. And same as about an hour ago, the main part of the proof is constructing a map and then using cofibration sequences. So we need to construct a map either in this direction or in this direction, and we also want this map to be functorial in some sense. Well, well, suppose K and A are subpolyhedra. Also suppose that the intersection is empty and the union does not contain some fixed point of the n-sphere, which we call the infinity. Well, let's identify the rest with r to the nth, and now we want to construct a map K cross A to S n minus 1. And then this is not quite what we're after, but we will use this map to construct the morphism we want to construct. Anyhow, so we well, the map is the first map we use is very easy. We just take the difference of the two arguments and normalize. Very well. Well, let's see what this map gives us. Okay, so my claim is we can use this map to obtain this one, and let's think. So let's start with okay, so let's suppose we have a map so this is what we want. Suppose we have a map from K cross A to B, then we have a map from K join A to the suspension of B. Now, the suspension is familiar. What is K join A? Well, K join A is the homotopy pushout of which is the same as the usual pushout of this diagram. Now, does everyone know what the join of two spaces is? Jipping. Okay, let's recall that I suppose to simplify, suppose we have AB inside of Rn. And suppose that those subsets have this property. If we take the line segments from a point in A to a point in B, these line segments will be disjoint unless one of the vertices one of the endpoints are the same. So in particular, the subsets themselves are disjoint. Then A join B. Can be viewed as the set of all the union of all segments, line segments, which start somewhere in A and end somewhere in B. For example, the join. So suppose we have SK and SL. What's the join? Can anyone tell me? Okay, so Alexei says it's A, K plus L plus 1. Okay, so one way to see this would be to well, to take Sk plus L plus 1 to be the unit sphere in R k plus L plus 2. Now, we inside it we have the sphere Sk, which is given by requiring the last L plus 1 coordinates to be 0, and similarly for the sphere SL. And then we use this procedure, and the procedure says that the join, which is the union of segments, is in fact the whole of the sphere, where we identify each segment from a point here to a point here with the corresponding spherical segment. So we have SL, SK, K. And and then we can take the straight line segments from a point of Sk to a point in SL, or we could take the spherical segments. And if we take the spherical segments, we'll literally get the sphere. And if we take the straight line segments, we get well, something homeomorphic to the sphere, but not identical to it. Very well. So we one of the ways to define the join is to use this homotopy co-limit or homotopy push-out, which is the same as the usual push-out because everything is cofibrant and both arrows are cofibrations. Very well. So now, suppose we have K cross A goes to B. Well, I also have we also have this diagram, which where again everything is cofibrant and all maps are cofibrations. Well, by comparing the two, we see that if one diagram maps into the other, then the homotopy co-limit goes to there's a map between the homotopy co-limits. Well, we have a map from K cross A to B, which is given. Okay, so we can extend this map by linearity to K cross CA. We just take the vertex cross K to the vertex of CB, and then define the rest by linearity, and the diagram strictly commutes. So everything commutes on the nose. So there's a map of the co-limits, and those co-limits are homotopy co-limits. Okay, so if we have just any map from K cross A to B, we have a map from K join A to sigma B. Well, the next thing I want to say is that K A is homotype equivalent to sigma Ka, which is the same as 1 Ka. Well, it's not really too hard. Basically, there's is there a map in either direction? Let's ask ourselves. Well, for example, we could use the same trick for the map from K to A, from K cross A to K wedge A. Then what do we get here? Here we get the suspension of the wedge. So there is a map in this direction. Does everyone agree? And all fibers are contractible. And if both K and A are finite polyhedra, then the map is also proper. So a proper map with contractible fibers is a homotype equivalence. Although in general, maps with contractible fibers need not be homotype equivalences. Okay, so we have this map. Okay, so we do not have a map from K wedge A to Sn minus 1, but we have a map on the level of the suspensions. And for spectra, this is good enough. we know this formula. Why is it true? We know that X wedge the suspension of the suspension spectrum of K. Is the same as basically suspending smashes with smashes of the components of X. So if X is if X is an arbitrary spectrum, to get the spectrum X wedge the suspension of K, it suffices to smash the components of X with K. This we know. Now, X itself can be suspension a suspension spectrum. So we could define the suspension spectrum of K smash A, where K and A are subpolyhedra, by taking the smashes of the suspensions of A with K, or in fact the other way around. So the functor sigma infinity is in fact monoidal with respect to the smash monoidal structure. Okay, so what do we get? We get a map from sigma infinity minus sigma infinity plus 1 K A sigma infinity Sn. Does this notation make sense? And if it does everyone agree? So we take this map that we've just constructed. We apply the the functor sigma infinity, and we get this, where sigma infinity plus 1 denotes sigma infinity of the suspension of this. Very well. So since so the suspension is invertible in spectra, we get sigma infinity k wedge sigma infinity A goes to sigma infinity S n minus 1. Well, what is this? It's the same as the sphere spectrum. Shifted by n plus 1 to the left. Okay, so the 0th component of the shifted spectrum. No, it's like this, n minus 1. Okay, the 0th component of this spectrum is the same as the n minus 1th component of the sphere spectrum, which is Sn minus 1. Okay, so so what do we have? We have a map from something smash something into something. What does this give us? This gives us a map from sigma from the suspension of k to okay, let me put it like this. From the suspension of A to F, the suspension of K, S, n minus 1, or which is the same as the dual of X, because X is just the suspension of K. The dual of X shifted by n minus 1. Okay. So minus n minus 1 dx. Basically, I formally do the opposite shift on the left. This is allowed. Is this what I promised? Так, я вот это обещал, или я обещал то же самое, но с противоположным знаком? Ну, потому чтобы доказать, что, то есть, нужно для начала нужно построить соображение, потом можно будет спросить, является ли оно изоморфизмом. So we have constructed a map from one spectrum to another spectrum, and the question is this an isomorphism? And we proceed more or less in the same way we just did in a similar situation. Well, firstly, let's look at whether or not this map is functorial. Well, first let's consider a simple case. Suppose we have x inside x prime, and well, and suppose we have the opposite inclusion for complexes which are or subpolyhedra which are homotype equivalent to the complements. Now, if x prime does not intersect, x prime is the bigger of the two, does not intersect A, and the union of the bigger element of each pair is inside Rn, and Rn is inside Rn is the same Rn we used just a few minutes ago. Then what? Then this map. And we have the this diagram which commutes basically by the construction of its ingredients. If we assume this, then everything works basically as more or less by definition. Now we need to see what happens if if we if x prime this time is allowed to intersect A, then we just remark that well, let me just informally say that one sorry, x prime k okay, so this is I'm sorry. Okay, so the polyhedra are denoted K, and I'm writing X's, and nobody is objecting. Okay, suppose K prime is allowed to intersect A, then one can pass from K A to K prime A prime by small changes. In other words, one can increase K while decreasing A, little by little, so that we have this we have this condition. And then the composite maps will be the map of the duals will be a composite. The map of the A's will be a composite, and basically the same diagram will commute. The diagram will still commute. So we what do we know so far? So far we have defined we have fixed an n and defined a map for subcomplexes or subpolyhedra of Sn. Now, does this suffice us to conclude that okay, so well, dx is pretty much canonical. We take the Hom into the sphere spectrum. Now A is the complement. Is the complement of K in some sphere. And a natural question is A canonical, meaning does the left-hand side of this arrow and the arrow itself depend on the way we embed X in the sphere. So we have okay. I will. So what? Okay, so this is the same as infinity minus n minus 1 of A. No, sorry, the other way around. Let me write it like this: infinity minus n minus 1 of A. Так, что-то запутался со знаками. Значит, помогайте. Скоро закончим. So here we had the suspension of the n-1 sphere. Okay, now here we need to have so okay, is this equality all right with everyone? Please pay attention, or we will get the wrong indices at the end. Okay, so we have a map from infinity minus n minus 1a to dx depend on well, of course it does, but if we have two embeddings in some two different spheres, it's a way to identify the two maps. Well, let's see. Suppose we have x inside Sn and inside Sm. Then we can always embed the two spheres equatorially in some S capital N, such that both composite maps become isotopic, which is basically the standard argument that I mentioned of. Oh, sorry, I'm using X again. K. If the dimension is high enough, then homotopy is the same as isotopy, and all maps into Sn for n sufficiently large are homotopic and actually null homotopic. Well, and again, if n is sufficiently large, all maps from K to any two maps from K to L are isotopic if and only if any two embeddings are isotopic if and only if they are homotopic, and they're homotopic because everything is. Okay, so basically we need to see what happens if if we take a K and then embed it in Sn plus 1 by using the composition with the equatorial embedding. Then then my claim is nothing happens. Then the map we get the suspension of A instead of A, but otherwise we we just compose this map with the suspension isomorphism to get a map for the new A. So we have two things, and those two things are suspension isomorphic. Okay, so the conclusion is we have constructed a map, and this map does not depend on the way we embed we embed X. And basically, I know everyone is tired, but just 5 more minutes, and then we'll finish. To finish the proof, we use the following remarks. The first one is something we already saw. And the second one, if we have a cofibration sequence of polyhedra, then the complements, one can choose A homotype equivalent to Sn minus k, B homotype equivalent to Sn minus L. So K contains L, so A will be contained in B, such that we have a similar co-vibration sequence for the spaces homotype equivalent to the complements, and then all we need to check that the map that we want to prove, for which we want to prove that it's an isomorphism, is part of a map of two co-vibration sequences. And okay, so basically the idea is to do an induction on the number of simplices in the polyhedron K, and it looks like no one's basically everyone's tired, and we should finish. So, are there any questions? Good. And this is it for today. And